Okay, so in this video, we're going to be taking a look at equations of planes. So just to get a little perspective on how that works, we're going to just do a quick little review of a vector equation of a line and just remind you of a couple of the main concepts. So remember, a line consists of an infinite number of points, and the equation represents a way of finding all those points that are on that line. So you have the generic location of each point on the line is equivalent to finding a specific point on the line and drawing a position vector to that line, that one there, and then following a particular direction vector, which is not drawn here, but you could draw a quick little direction vector. So follow this direction and take a scalar multiple of that direction vector, and you'll be able to locate every point on that line. So even though the direction vector is pointing in an upward direction, you can use a negative scalar multiple to then locate all the other points. So as long as you can get to a point on that line and use the direction vector and a scalar multiple of which, you can find all the points on the line. That's how you come up with your formula. In a plane, a way of thinking of the plane is like a surface, like a desktop, or actually a sheet of paper actually works well because you can hold it up in the air because you can tilt it in different directions. So there's a little activity that is in part of the lesson that's on the Google Drive for you to access. I'm just going to quickly show you how this works. So suppose this entire white surface is a plane. So think of it as a big sheet of paper. And on it, we've got 3 different points. So just to make sure you understand what's going on, so you have 3 points, but they're not collinear. You want to be able to use vectors drawn from A to C and A to B, use scalar multiples of AB and AC to get to point D. Well, let's see how this would work. So I could take a representation of B and add it, or sorry, AB and add it to AC. But as you can see, I'm going in the wrong direction. So what could I do? I can get a negative scalar multiple of B, roughly that. And even if it's the opposite vector, I'm getting closer to D, but I can scale that down a little bit, or even leave it as is, just to show you how this would work roughly anyway. And then take a version of B, or sorry, AC. So just to show you how this works. So even if I had to extend the magnitude of vector AB in the opposite direction, and then I could use AC exactly, and I'd be able to get to point D. So it's a matter of using scalar multiples of one vector, so K multiplied by vector AB, and then adding vector AC. Okay, and that would give us a pathway to get to D. Now the idea behind a plane is that, well, that gets us to one point. How do I then come up with a formula to find all of the points on this plane? So again, keeping in mind that D is a point anywhere. So I could have a point that is over here. How could I use vector AB and AC to get here? How could I use vector AB and AC to get there? How could I use it to get there and there? So the same formula or calculation has to work. But the key thing is, to be able to get from one point to another, I need 2 directions and scalar multiples of it. So unlike the line, there was only 1 scalar multiple of a direction vector to get in the line. Now I need 2 directions to be able to start at one point and get to another point. And that's the idea behind defining a plane, is that you can get from one point to another using 2 separate direction vectors and scalar multiples of them. And that defines your plane. So that's essentially how this works. So vector equations of a plane look like this. You have a position vector to an initial point on the plane, on the surface, and then you have scalar multiples of two different direction vectors. So this will look a little bit more familiar in component form. So again, the generic vector x, y, z is a combination of a position vector pointing to a specific point on that plane or surface or sheet of paper, and then adding scalar multiples of two direction vectors. Okay, so the A1, A2, and A3, B1, B2, B3, these are referred to as direction numbers because they're part of the direction vectors. So since you can write a vector equation using component form, much like with the equation of a line, you can then write parametric equations. Okay, so the x, x naught, SA1, TB1, and then similar pattern to get the other remaining parametric equations. All right. Okay, there is a scalar equation of a plane in 3 space. Okay, and it looks like this. And obviously you can look online to get proofs and whatnot, but we're going to just jump right into it. And much like the line, the normal vector of the plane is the coefficients listed for the A, or for the X, Y, and the Z variables in the equation. Okay, so a sample problem, just to kind of, there you go, it's a little bit better. Sample problem here, find a vector and parametric equations for the line, sorry, for the plane containing these points. So again, much like that intro example, you have points A, B, and C. We're looking at finding vector and parametric equations. So the generic formula is to take a generic vector pointing to the plane. Now, here's where things get interesting. So you choose any one of these points as a point that's going to be used for the position vector to a specific point on the plane. So it could be any one of those 3, right? But then you need direction vectors, 2 of them. So much like in that intro example, I can have a direction vector from A to B, and then a direction vector from A to C. And again, how do we find those direction vectors? Well, it's just subtracting the components. So direction vector from A to B, 0 take away 4, 1 take away 1, 2 take away -1 to produce that, and similarly for the direction vector A to C. So there's your vector equation, right? Pretty straightforward. Parametric equations, again, very easy, just connecting all the X, Y, and Z components. Okay, so in this particular case, the y simplifies to a y equals 1. So this is simplified, this is now simplified, and this is now simplified. But I do encourage, when you're doing this sort of technique, to write it all out first and then worry about simplifying it later. Right? Just becomes that much easier. So again, this is a way of finding all the points on that surface, on that plane. Again, if you're holding a piece of paper in the air, you can think of the corner of your room as the origin, and imagine a vector from the corner of that room to a specific point on the piece of paper you're holding in the air. Okay? That would be this. And then on your piece of paper, you would have 2 direction vectors that will allow you to find all the other points on that piece of paper. Now, what you have to kind of envision also is that piece of paper that you're holding that represents the plane goes on infinitely. Obviously, the piece of paper you're holding doesn't, but that's what you would have to kind of imagine to visualize this whole thing. Okay, now, so why do points A, B, and C in this particular example not determine a plane? So just because you have 3 points doesn't mean they're going to determine a plane. Well, they're more than likely collinear, because again, what you're looking for is you need 2 direction vectors to define a plane. And if you can't get 2 direction vectors out of these 3 points that are not collinear, then you're not going to get a plane. So there's different ways of showing this. You can show that they're on a particular line. There's method 1. You can use your dot product to go ahead and show that. So again, we've looked at collinear aspects before. The more textbook style solution, at least the textbook that you folks have been using, is once again showing that there's a scalar multiple between vector A, B, and AC. Okay, so proving that, showing that AB is a scalar multiple of AC, just involves setting up the equation, and then, so that means that 6 must be equal to negative 3k, 2 must be equal to negative 1k, and 4 must be equal to 2k. So this must produce the same k value, and it does. K is actually equal to 2 in this case, or sorry, negative 2. So that tells us that AB is a scalar multiple of AC, so that means that A, B, and C are collinear, so it cannot form or determine the plane. Okay, so that's just something to keep in mind. Okay, explain why the line and the point do not determine the plane. So this is a little bit more interesting because as far as the 3 points that I talked about before, so a line already has a direction vector. Okay, so to visualize what's going on here, your line would actually have, let's just something like that, and then a point. Oops. So why wouldn't that create a plane? So let's take a look at the question again. Why does it not determine a plane? Well, I need one direction vector, which I can get from there, and I can get a second direction vector, something like that. So what must be true about this point? Well, this point must be on the line. There's that collinear aspect again. Okay, so if that point is on the line, then I'm going to wind up getting only one direction vector and not being able to get the second direction vector. Okay, then that's how that is visualized, and that's where this logic of if the point Q is on the line, then the line with Q does not determine the plane. Or sorry, the line and the point does not determine the plane. So how do you prove that? Well, you can get some parametric equations from the line and solve for t, but you're looking at equating these parametric equations with the x, y, and z values of the point. And if you do get the same parameter, then that tells you that that point is actually on the line. Therefore, it cannot define a point. Or sorry, the line and the plane point cannot determine the plane. Okay. So there are also some other examples you can take a look at in section 8.2. They're extremely important for you to take a look at. Modified the practice problems for you to work on just to provide a little bit more focus. Okay, so again, here's the visual in terms of the direction vector. So again, what happens if point Q is on the line? Then you're only going to get one direction vector. This is the scenario you want. You want Q to be off the line to be able to get that second direction vector. Okay, so hopefully this brief little video is helpful in explaining some of the aspects of the concepts of equations of planes.